Welcome to this engineering hydrology lesson. Today, we're going to solve a problem about designing a trapezoidal irrigation canal. Let's start by visualizing what a trapezoidal canal looks like. A trapezoidal canal, as the name suggests, has a cross-section in the shape of a trapezoid. It has a flat bottom with width b, a depth of water d, and side slopes that rise at an angle. In our problem, the side slope is given as 1:1, which means for every 1 unit vertical rise, there is 1 unit horizontal run. Now, let's identify and organize the parameters given in the problem. We need to design a canal that can carry a maximum discharge of 8 cubic meters per second. The cross-sectional shape is trapezoidal, with a side slope of 1:1. The bed will be lined with concrete, and the bottom slope is 0.0005. The permissible ratio of bottom width to depth b/d is 3. Our job is to determine the appropriate design depth of the canal. One parameter we need for our calculations that is not explicitly given is Manning's roughness coefficient, N, for a concrete-lined canal. A typical value of Manning's N is 0.015. We'll use this value for our calculations. To solve this problem, we'll use Manning's equation, which relates the discharge to the geometric and hydraulic properties of the channel. Manning's equation is Q equals 1 over N times A times R to the power of 2/3 times S to the power of 1/2, where Q is the discharge in cubic meters per second, N is Manning's roughness coefficient, A is the cross-sectional area of flow, R is the hydraulic radius, which is the ratio of the area to the wetted perimeter, and S is the slope of the channel bed. For a trapezoidal channel with 1:1 side slopes, we need to express the area and wetted perimeter in terms of B and D. The area of a trapezoid is the average of the top and bottom widths multiplied by the depth. For our 1:1 slope, the top width T equals B plus 2D. So, the area equals B plus 2D plus B divided by 2 times D. Simplifying, A equals 2B plus 2D divided by 2 times D, which gives us A equals B times D plus D squared. The wetted perimeter P is the sum of the bottom width B and the 2 sloping sides. For a 1:1 slope, each sloping side has a length of square root of 2 times D using the Pythagorean theorem. So, P equals B plus 2 times square root of 2 times D. Now, we can express the hydraulic radius R. R equals the area divided by the wetted perimeter. Substituting our expressions for A and P, we get R equals BD plus D squared, divided by B plus 2 times square root of 2 times D. We know that the ratio B divided by D is 3, so B equals 3D. Let's substitute this into our expressions. The area becomes A equals 3D times D plus D squared, which equals 3D squared plus D squared, or 4D squared. The wetted perimeter becomes P equals 3D plus 2 times square root of 2 times D. And the hydraulic radius R equals 4D squared divided by 3D plus 2 times square root of 2 times D. Simplifying, we get R equals 4D divided by 3 plus 2 times square root of 2, or approximately 4D divided by 5.83. Now, we can substitute everything into Manning's equation. Q equals 1 over N times A times R to the power of 2/3 times S to the power of 1/2. Substituting our values. 8 equals 1 over 0.015 times 4D squared times 4D over 5.83 to the power of 2/3 times 0.0005 to the power of 1/2. Let's simplify this step by step. 8 equals 1 over 0.015 times 4D squared times 4D over 5.83 to the power of 2/3 times 0.022. 8 equals 66.67 times 4D squared times 4D over 5.83 to the power of 2/3 times 0.022. 8 equals 5.87 times D squared times 4D over 5.83 to the power of 2/3. 8 equals 5.87 times D squared times 4 over 5.83 to the power of 2/3 times D to the power of 2/3. 8 equals 5.87 times 4 over 5.83 to the power of 2/3 times D to the power of 2 plus 2/3. 8 equals 4.6 times D to the power of 8/3. D to the power of 8/3 equals 8 over 4.6, which equals 1.74. Taking both sides to the power of 3/8, d equals 1.74 to the power of 3/8, which equals 1.22. So, the design depth is approximately 1.22 meters. Looking back at our options, the closest to our calculated value of 1.22 meters is option D, 1.2 meters. Let's verify this answer by calculating the discharge, with D equals 1.2 meters to ensure it can handle the required 8 cubic meters per second. With D equals 1.2 meters and B equals 3D equals 3.6 meters, the area A equals 4D squared equals 4 times 1.2 squared equals 5.76 square meters. The hydraulic radius, R equals 4D over 5.83 equals 4 times 1.2 over 5.83 equals 0.82 meters. Using Manning's equation, Q equals 1 over 0.015 times 5.76 times 0.82 to the power of 2/3 times 0.0005 to the power of 1/2. This gives us approximately 8.01 cubic meters per second, which confirms our answer. Therefore, the correct design depth is 1.2 meters, option D. In this problem, we used Manning's equation and the geometric properties of a trapezoidal channel to determine the required design depth. We found that a depth of 1.2 meters will allow the canal to carry the maximum discharge of 8 cubic meters per second while maintaining the required B/D ratio of 3 and other given specifications. This channel design will ensure efficient water flow in the gravity irrigation system.